Cat.
Oh, that's going to cause trouble here. Oh,
This one, or we can give you the one for the pod.
just because I'm going to stumble over this.
Yeah,
I'll do that. Okay, thank you for having me. It's great to be here. Great workshop, great food, great science, and at the right time, as you all agreed for this week. So I'll talk a little bit about machine learning for LHC theory. I'm limiting this a little bit to theory, even though you see actually it's more like what theorists do rather than proper theory. So like, the first half is going to be like mostly experimental. One thing I think that's important also, like, with the Nobel Prize, everybody's like, asking us about that. And we're still domain scientists. I mean, I still care more about dark matter and matter antimatter asymmetry and like the origin of the Higgs boson than about like, computer science problems with machine learning. But we all know that we need to solve those problems. We need machine learning. And let me just like, tell you very briefly, because it's a very broad audience, what LHC physics is all about, in my view. So LHC physics is all about fundamental questions, like these three, and add your favorite one to that, right? And then it's about very, very big data sets. Like, it's Atlas produces petabytes a second. I mean, we only like, I think, ever look at 1 in a million or less, or they, but like, it's petabytes a second. So it's very, very big data sets that we want to thrift through. And then what we have, and I think that's really cool in particle physics, we have these first principle, like precision simulations. So event generators and detector simulations, and we have complete control over uncertainty. And we actually do have, like, as particle physicists, a little bit of a fetish with uncertainty control, as I'll tell you in a minute. And that actually affects the way we think about neural networks, I think. And we have a very successful past where we measure total rates. Everybody at Atlas, and they're measuring a lot of total rates. To me, it's a little bit unclear why they do that, because I don't remember the last discovery we made in measuring total rates. Must have been before the JSI, is my guess, but I really don't know. But we still measure total rates and we feel good about it. And then we have analysis, which are essentially inspired by like models and simulations. So like, some theorist that comes up with a model, we simulate, the experimenters look for it, and they never find it. And that's like, a sexual path. Actually, it worked for the Higgs, and it worked for absolutely nothing else. It also worked for the top quark and the tevatron. And I do think that we have to slightly rethink that, and machine learning is the way to rethink that. Am I being recorded and like broadcast right to CERN? So, and I think what we want to, if you want to like rethink that, I think what we should do is we should think about our strength, and that is these simulations. And like everybody's talking about that, like, outside physics, we call it digital twins, or whatever you want to call it. In physics, we call it simulation-based inference. In cosmology, the same. So you start, in our case, with a Lagrangian, you calculate scattering using quantum field theory, and then you simulate these collisions, and then you simulate the detectors, and then you actually have a data set of LHC collisions in a virtual world defined by the Lagrangian, which means the Lagrangian particles and interactions put in. And those you can then compare. I mean, so you can compare these like simulated events with the real events, like event by event, if you want, right? Petabytes a second. And then we can redefine our searches for new physics, because whenever these two data sets agree, there's no new physics. And when they disagree, we have a look. And if they disagree, probably our simulation is wrong, or the detector is doing something funny, but maybe there's then new physics after we have like excluded these other like, explanations. And this is really what we want to do. And if you think that way, you see, where data science or machine learning fits into this method, because this is about, as I said, digital twins of LHC events that we're going to look at. I like digital twins because our medical people use that term a lot and they get lots of money for it. So I'm trying to like ride on their wave. And this is our forward simulation chain here, by the way. This is from theory like Lagrangian. We do this entire simulation. Notice this very slight bias where 1, 2, 3, 4, 5 in the hand of theorists, and then the experimentalists do that. When experimentalists make the same figure, it's theory, experiment, and the last line of their code. Okay, fine. This is the bias, but we agree on the link between theory and events. Okay, and what's the role of theory? And I think that's important to explain to people, because nobody essentially knows that. Is that in LHC, at least high PT, like Atlas CMS, physics. The simulations are really in the hand of the theorists. We do the simulations for experiment. In other fields, I am aware of the fact that that is different, but I mean, it doesn't matter who does them. It generalizes. It's the simulation people, right? And in our case, they're theorists, so they start with this Lagrangian, and they generate Feynman diagrams. And then compute the hard scattering, like, the 2-to-2 scattering, like, glue goes to TT bar, top, anti-top, right? And then the top decays to like WB, and the B decays, the B decays to whatever leptons and a bunch of like later hadrons and so on and so forth. And there's jet radiation, like, radiating quarks and gluons all over the place. And then the harder stuff, like, for instance, the protons actually like consist of quarks and gluons. We need to describe this somehow through parton densities, or like, we need to describe hadronization. There was a nice paper out today, by Slovenian Yugoslav and his friends, like, on that one. And this is all, but that's important. What we want to do is, and now here comes a language problem. I call this first principle simulations. I said not modeling, except that everybody else in other fields calls modeling first principle simulations. So, but I really mean first principles. I mean, put a Lagrangian and simulate. And if you think about the detector, put the building plan of the detector and the materials in the cross-section and simulate, because we can do that. Right? We want to avoid, like, just describing stuff. And the challenge for the high luminal LHC is that we discussed this yesterday, like, the LHC, like, will end around, I don't know, around 2040 or something, depends, like, we'll see. But like of that data set, we have 10% on tape right now. So like all that depression where people say we're in a crisis, it's like bullshit. I mean, we have seen 10% of the data. We really have absolutely no idea what the final data set will tell us eventually, right? But that means from now and to the end, we need to, like, we have statistical uncertainties which are a factor 3 smaller, right? It's root 10, which means our theory predictions have to be a factor 3 better, which means 1 order in perturbation theory. This is a huge amount of work, and it's really, really big effort simulation-wise. That means I want to estimate the density over phase space for scattering to, say, per mil. So my networks have to understand the network, then the density over phase space at the per mil level. If I don't do a per mil, the theorists will tell me it's not good enough. And then we do simulation-based inference. And as I said, simulation-based inference, the S for all experimentalists, the S stands for simulation, for theory. So like, we have to get that right. And the advantage that we have is that in quantum field theory, speed and precision, like, are the same thing. So if you have much better computers, you can actually, to first approximation, go more precise. So like, at least for us, on the physics side, speed and precision are the same thing. And then, like, we'll have these event generators. We call ours Madness. MadGraph is our current generator, and this one is the new version. It's called MadGraph Neural Importance Sampling, or Madness. And the other simulators have the same thing. Okay, that's our goal. I thought, like, that talk fits really well in with the last speaker, because I told you about our like a little like soft spot of uncertainties. So like, what about these uncertainties? And I'm going to give you an example how we can actually train neural networks with uncertainties. And I think like you'll see a lot of the formulas are very, very similar, even though we are a bunch of frequentists, and this is just really just learning with uncertainties and variational inference. So this is much less abstract than when you've heard before, but it's the same formulas, I think. So if you think you want to calibrate the Atlas calorimeter, which is funnily enough what I'm currently doing, right? So you want to calibrate the Atlas calorimeter. You want to measure the energy of a cluster or a jet J, right? And that any measurement is an expectation value over a density, E expectation value over, and then an integral over EP of E, right? And this is the definition of an expectation value, like statistics, right? Probability. The thing is, when you do this, like describe this through a network, what you actually write is you write this P of E as an integral over a internal representation, latent representation theta, and then you weigh the probability E given the theta represent point with the probability theta given the training data. Right? And this is really like, the statistical interpretation of a network prediction. And whenever we write these theta distributions, we call this a Bayesian neural network. It's just a name. But it's really like, something like, theta has a distribution. In the classical network, theta has just a value. This one here has distributions, and that's the difference. And when you train a network mathematically, I love this formula. It's like, this variation approximation. When you train a network, you take that formula here, the theta, P of E of theta, and then P theta given training data, you replace P theta given training by a universal function, Q of theta. This is now known. It doesn't depend on the training data anymore. It's encoded in the network. right? So there is no dependence anymore on the training data, and that means you can now evaluate a P of E as a function over an integral over theta, P of E given theta, some network parameterization, and Q of theta, which is the representation in the network. Okay, and you can think of Q of theta if you want. Now you can write down whatever you want, but that could, for instance, be a Gaussian with a mean and a width. That's the simplest approximation. You can actually make that more complex, right? And then P of E given theta tells you how you get an energy out of that. And in this definition of like training, you see actually comes here. You have like, to train, you want these two like functions. That doesn't matter. Oh yeah, you want these two functions to be the same. And you do that by like making calculating the KL divergence between those two, and you write this down. Here you actually put in Bayes' theorem. You saw Bayes' theorem earlier, and you get this expression here. So this has a KL divergence between this prior and between the prior in the Bayesian sense here and this Q distribution here. You have a likelihood term, and you have that. However, you can ensure that this, if the weights are normalized and log P of t doesn't depend on theta anymore, then for the loss function, just minimize the first two terms. And that's a likelihood loss, pretty much exactly what you said. This is how you train a network with uncertainties. So every network has a two-term likelihood. That's a loss of, here. This is a prior term, and this is a likelihood. So what does this mean? I mean, the prior. Well, let's write it down, right? The prior is, I just copy this formula. Let's assume that I have two Gaussians, because two Gaussians is the only function where I can actually write the KL divergence in closed form. You write this down here, and you put it in, and you see that really looks like an L2 regularization, for your terms. So if you now go and you make these network weights, replace the distributions by individual weights with the theta function, you find that this term here becomes a likelihood term, and then it becomes just this theta naught here. L2 regularization. So this thing that we call the prior, dependence, how you call it, is nothing but an L2 regularization. It's just a general L2 regularization. So you get that for free. It comes out of the training. Or in other words, the appropriate regularization of the network could, in this ansatz, would be an L2. So how do I think of this Q of theta? I mean, people have thought about this before, and other people, but not with the Gaussian, but with Bernoulli distributions, then we call this dropout. Right? So this is, if you want, a generalized dropout. So what we have is we have networks which learn a value and an uncertainty. They're regularized by default, and they have dropout, which means they don't overfit ever. Right? This makes them so powerful. And how do I evaluate it? I've evaluated this network now. I just wrote the same expectation value as before, and I switched swapped the two orders of the integration. So now it has a theta sampling step here, and this E bar of theta includes the energy integral here. That's just writing that definition. What's important is, if that is an expectation value, you can write down the variance of it, or the standard deviation, which then has to be that. That's by definition, right? If this is the expectation value, this is the variance. Right? And now you can play one trick, and you can split this term here, these three terms, into two contributions, which by definition add in quadrature. And I'm don't want to write down these two forms, but what's important is they have two different, you have two different contributions to the variance or the uncertainty. One is the case what I call statistical here, something that vanishes for perfect training. If you you have trained your network such that the width for theta, is negligible compared to the value for theta, all right? Then you have you get one, and you have only this term here left, and that term vanishes. This is why we call the thing that vanishes in that limit statistical uncertainty. And then you have the other uncertainty that doesn't vanish for a lot of training, but it would vanish if your data were perfect. No stochasticity, everything works perfectly. We call that a systematic uncertainty. And we can do that. And so I just want to say, these are the powers, and when physicists think about neural networks, these are the things we can do with neural networks. It's much, much more than just predicting a number. And I'm not going to talk more about this. All I want to say is, we use that exactly description currently, for Atlas calorimeter calibration. So, this is in particle physics, this is actually being done. This is what Atlas puts with the help of theorists, put into there. This is how we calibrate stuff now. So this is a regression with an error bar. And we study these uncertainties in quite some detail. So, and I think this is if anybody ever wants to work with these kind of things, yeah. On the other hand, we know that regression and let me skip classification, even though classification is the basis of every LHC analysis. But fundamentally, it's boring because classification is just the same as regression, just you're learning a function that's a probability, right? But it's still like it's a function, it's a scalar function. And I should say, classification is like one of the things where, like, you know, LHC physics, everybody is using neural networks. There's not even a discussion anymore if you want to do this, like tagging, identifying what's in a jet. But technically, it's not that interesting. Technically, more interesting is generative AI. And let me just, like, you know, my story of generative AI, I started, like, you know, looking into this, like, you know, close to 10 years ago. And I think we have gone through the entire, like, waves of generative models that everybody hypes. So we have started, like, variational autoencoders earlier on, noticed that they don't work for us. And then we did GANs. We love GANs, but problem is, you see, GANs are networks which have, like, you know, have a game theory background. So a discriminator and a generator have to agree, or make a compromise on what a good description is. The problem is, like, that, as always, like, you know, two players can come to a really garbage compromise, and, like, you know, and then it doesn't help. And this is actually the limiting factor of GANs. You know, they agree on something, but what they agree on might just be crap. And then you have no way of telling them that. You know, you cannot send them back and say, like, think again. What's much better for us is normalizing flows or diffusion models. I put them here into one category because they're much more precise. And then the latest stuff that, like, people looked is, like, you know, is transformers, JetGPT. So we coined this. I'm very proud of this, like, you know, JetGPT term. I wrote an entire paper just to be able to put this term into the title. And then vision transformers, which are used for detector simulations right now. So people are using transformers now. Recently, like, we started working on equivariant transformers because in particle physics, you know, we actually know our symmetries better than, like, I mean, we have symmetries all over the place, and so, like, it makes sense to include them. And now we, like, combine this all, like, equivariant transformer conditional flow model matching models. Like, you know, this is currently, like, what we're using. We're basically picking from all of these things because we need performance. Okay, and uncertainties for the generative networks. I told you uncertainties we can do with Bayesian networks. It turns out, I don't want to discuss in, like, you know, too much detail here, but it turns out that you can actually use the same uncertainty description that we use for the regression or classification network for generators. If you define the uncertainty of a generator as the uncertainty in the underlying density estimation. So basically say, I learn the density, and that learned density has an uncertainty, and then I sample. And the sampling uncertainty will then not be, like, you know, treated, like, you know, covered by this uncertainty measure, but the underlying density estimation you can. And then, like, you know, we discover these kind of things, and it works. Let me just say it works because I want to move on a little bit and show you how it works. So here, for instance, we have LHC simulated events. This is basically a Z boson plus one jet, and this is the transverse momentum of one of the jets. And this is a typical kinematic distribution of the LHC, drops, like, you know, three orders of magnitude between transverse momenta of 25 and 150 GeV. And what I want to show you here is that is the deviation of the, like, the learned density from the truth. And you see that the blue line here, like, you know, it agrees, but, like, you know, a certain percent overestimate here in the tail, which is fine. You don't have enough that much training data. Also, there's some wiggles here due to a lot of training data. What's important is that the light shaded blue region here is the uncertainty measure, and you see that it nicely covers the one here. So, like, you know, the network knows it's not perfect. It knows it has not seen enough training data, right? So we can actually use these networks to generate events and be aware where our training data was not sufficient to be as precise as it should be. We can also do systematic uncertainty. I love that part. So, like, you know, imagine you know your simulation is garbage in some phase-space region. What do? Well, what you can do is you can take your simulation and introduce a toy parameter A here, and you basically weigh your events. You say, like, I'm not very sure how it is, and so, like, let me introduce an error bar on the simulation in the weight. And then you learn from those events conditional on this parameter A. And then you sample your events and you sample A. And then you basically get the uncertainty covered. It's covered. It's like a nuisance parameter, right? And then we, like, you know, get these kind of, like, you know, uncertainties here, theory uncertainties. So if your something is not perfect and you know it, you can simulate it. So, like, you know, this is our, like, you know, focus on uncertainties. That's all technical. Now, when you talk to people, especially now, especially since 2 days ago, like, but even before, some like university, like, vice president will always come to me, that's my friend, like, the physicist, vice president, said, where does machine learning really revolutionize particle physics? They always want to know this answer, right? And then saying we do everything much better is not sufficient, right? I mean, they want to hear more. Let me tell you one thing where, like, I think machine learning does revolutionize LHC physics, and that has to do with inverse simulations or unfolding. And it's just one of the examples. It's my favorite one. So there's two reasons why the way we currently do analysis at the LHC is not actually going to, like, generalize to high lumen LHC. The first one is, if you do simulation-based inference, you need precision simulations for the signal and for the background, right? This is what simulation-based inference implies. But theorists come up with new models way faster than we can include them in our Monte Carlos. So it is simply impossible to generate, like, signal simulations at the required precision. Background we can do, because background doesn't change over time, but signal change every week if right? Somebody comes up with some model. Actually, theorists have no idea when they come up with this model that this is a huge challenge and how much brain power and experimental side we burn by coming up with a model. So we move on. Like, a week later, we have a new model. And we do not actually appreciate the fact that some poor students in experimental physics is going to spend 3 years on our first model. And we have long moved on. So we need a different way to do analyses. Now, a lot of these simulations are burned in the simulation time is burned in detector simulations down here. So why can I not do my tests rather than on events here? Why can't I just turn my events after detector into events before detector through an inverse simulation, so an inversion, and then do analysis much cheaper? Or you do it somewhere here where, like, theorists can do it themselves. You don't even have to spend your experimental graduate student on it. You basically say, theorists, run MATGraph and you get it out. The second thing is optimal analysis. It's not at all clear that the best theory predictions actually make it all the way to here, because some people might just calculate some stuff at higher loop order that is in no Monte Carlo, right? So, like, the best analysis might not be even here. We might have more powerful predictions here. The last thing is, there's a common law that says LHC experiment data is too complex or too complicated for you idiots, is what they say, right? That is true if you look at detector output. If you look at the stuff before the detector, the stuff that enters the detector is not that complicated. As a matter of fact, all the simulations tools for this are written by theorists, so that it can't be too hard for theorists because we describe it, right? So in other words, this is true, but if you accept the fact that nobody cares about the detector except that it works, right? If you do the analysis here, it's not at all clear that high school students in California cannot analyze this data. They can, right? Like, so do this unfolding and publish your data that way. It's more efficient, it's better, more precise, and everybody can do it. And how do we do this? This is, like, what machine learning allows us to do. And just a very brief introduction to unfolding. I'm doing time-wise. I'll be fast. I mean, yeah. Oh yeah, I don't need those. So unfolding is essentially a story of two conditional probabilities. And let me just describe this picture here once, because then we have it, right? So we have a simulation chain where basically you can call this here parton level or particle level. I don't care. This is before detector. This is after detector. And in the simulation chain, in our forward simulation chain, we have these kind of events. And you say put a detector simulation that gives us these events at the RICO level, right? This is what a detector or detector simulation does. And what they learn is nothing but a conditional probability x RICO given x part, right? I mean, this is what they do, right? I mean, what a detector simulation encodes in this direction, right? What's important is this is just a conditional probability. Now, imagine you have your data that lives in x RICO, and you want to use, like, go to back, like, to some earlier stage before the detector and do unfold the inference here. What you there need is the other conditional probability, right? It's x parton given x RICO. So it is actually symmetric. It's just two different probabilities, and they're related by base theorem, right? So, like, this is, like, they're statistically, this is totally well defined. What you need to know to see the simplicity and beauty of this picture is These kind of probabilities we learn from paired events. So like, how we train a fast detector simulation is we give it events in X parton and X Rico, and they're paired. They come from each other. So they encode how one gets like produced from the other. So we learn those from paired events. So these are literally paired, like one event here, pairs, you train the network for the condition probability. Now, if that is true and you can train this forward condition probability on paired events, clearly you can train this one here on the same paired events, because it's paired events. Paired events don't care about, like, these are joint probabilities. Like, they don't care about the condition, right? The only question is if the claiming that this simulation here agrees with that data gives you a bias, right? I mean, do these things really agree with each other? So like, that's the prior argument. But, so what I'm arguing is that forward simulation and unfolding is the same thing from a machine learning perspective. Now, we know that the detector isn't perfect, so there's a loss of information, but you know what? We are doing anything statistical or stochastic. Like, we never look at deterministic forward propagation, ever. And if, like, if you go further in our education, it's even quantum, so it doesn't even make sense to look at deterministic, right? So it's that information loss, and our detectors are pretty good. So, like, that information loss is technically negligible. It exists, and it will lead to a broadening, but it's technically negligible. And that means if we can use neural networks to train these two, like, conditional probabilities, this for forward simulation and that for backward unfolding in an unbinned and high-dimensional way, we can publish our data, because then we can basically publish that, and everybody can play with it. And I have to mention this. There's a famous paper. It's called Omnifold by two of the great heroes of machine learning and particle physics, Ben Nachman and Atlas, and Jesse Taylor, a theorist. And this is what they do. So they basically want to learn this probability here, or actually they want to get to this unfolding probability. What they do is they run a classifier between these two data sets on the same phase space, reweight them into each other, then pull and push these weights up and down here, transfer them out here to the simulation, apply them here, get that. So what they do is, through a classifier, ansatz, they actually they learn every single connection in this square except for the one that we care about. So like rather than going from here to here, like, learning this conditional probability that just introduced, they do this way and like here, over, up, and back over. And they do learn it that way. And this is actually being done by LHC experiments. So this is like, classifier driven unfolding. Atlas is doing that in 20-something dimensions, last Z plus jets physics. Right? And it's called Omnifold. And it's driven by classification, and classification is a tool that works extremely well. What I care about and be like, is I want generative AI. I think my favorite is just, look, Ben Nachman, and he just loves his classifiers, and he's the master of classifiers. So, everybody uses their tool, and we use our generative tool for the same thing. So what we do is we basically take paired data and we learn this as a conditional probability. The challenge here is, by the way, there's a couple of extra things that we need to think. The most important one is when we started about this with thinking about this with GANs were just not good enough to do it right. So by now we have these combinations of conditional flow matching and transformers which do that well. So let me give you an example here. This is my favorite example. I love talking about this also because it's actually unpublished data. So I show you some results which are currently stuck in CMS management, and they don't want us to publish it. But nobody has yet sent me an email that I can show them. And also, if they send me that email, what are they going to do to me? So what you want to do is you take top quark decays, and you want to you have the three jets, from the B and from the W to two decay jets, and you want to measure the top mass in the unfolded way, and you want to then publish the data. It's exactly what I advertise doing, and this is something that a friend of mine, Roman Kukla, and his group has done in CMS with classical methods. And they ask us, can we do this with the better methods? And let me just illustrate what the problem here is, because it has a cool problem. And that's the last problem, like I discussed. So the top mass is encoded in the simulation, right? Let me call that value MS, simulation mass, right? In the data doesn't know about our simulation and vice versa. So the data has a data top mass. If I learn this conditional probability from paired events, my conditional probability depends on MS, not on MD, which means my unfolded distribution depends on both. And what makes these, like, you know, these tools especially nasty, like, you know, this problem especially nasty, is that actually in the standard setup, this one here, this condition probability, doesn't depend on MD at all. So the result is in practice totally, like, you know, biased by MS. And this is, of course, not what we want. What we want is that MS here is negligible and MD features. And so this was, like, you know, the challenge that like, you know, our student here, Sophia, and the collaborators did. So what we basically said, we weakened the bias by training this here on a range of MSs and not telling the network there's a range of MSs, right? I mean, you can do this, just, you know, take 3 different values or 4, whatever, or range anything. And then we included some batch-wise information here when unfolding, like, you know, we basically said, like, you know, add an approximate version of MD to the data representation. And that did it. So here's our result. So this is the mass measurement of the top mass. So this is the triple jet mass that should give us the top mass. The generated data here, this is all simulations, not actual data, but it's full simulation of CMS, so it's all as good as data. The black curve is, you know, what the result should be, like, you know, before it enters the detector. This is what CMS gives us. The blue one is what it gets after the detector. So the detector smears it out quite significantly and moves it over. And our unfolded curve is red. So that's what we resurrect. And this is, by the way, with a data-driven top mass, not with a simulation-driven top mass. So the bias has gone. You can do this, like, you know, for all kinds of top masses. The ratio of the two is the red curve here. And you see the two distributions, even in the peak region, they agree at the level of 5% roughly. 5% is not 1%. I prefer 1% or 1 per mil, but it's a good start. For the experts, the top mass, the top decays to a W and a B, and the W has a mass as well, which, by the way, like, you know, CMS just measured incredibly well. So we want to get that right. So this is the W mass peak. We did nothing to the W mass peak. The W mass peak is what it is, right, in our unfolding. And you see that, again, black is put in, blue is what the detector does with it, red is what we get out, and it agrees nicely. This, by the way, is technically for the CMS analysis, the way they calibrate the analysis. They use the W mass peak. And then this one here is all kinds of correlations they get right. This is my favorite little top mass correlation plot. Like, you know, this is the combination of, like, you know, 2 different, like, you know, masses, top combinations, like jet combination, which could give you the W mass. So sometimes it's that, and sometimes it's the third combination. And this is where all the tops sit. And then, like, if you plotted this figure for unfolded data, it would literally be indistinguishable. You can run a filter on this. I want to work on CMS data next, but I don't know if I'm going to get there. Okay. Here's my bottom line. Here's, like, you know, we want to develop machine learning for the best science. That's our goal, right? You know, I would love to say, like, I'd like to get the Nobel Prize for machine learning and physics, but that's gone. Like, screw it. So it's just another numerical tool for numerical physics. I always say this. I always say. So I always say, when they're senior people, I say, it's just another numerical tool for numerical physics. Don't worry. This is what we tell our senior colleagues, right? We also know it's a lie, right? It's not just another tool. It's going to change the way we do physics, but we can't tell this to our senior people, because then they're very scared and they cry. And we don't want this. We don't want people to cry. So we just say it's just another numerical tool, knowing that we lie. Like, you know, it's a numerical tool that transforms the way we do science, I think. It also transforms the way that we can communicate, because look at this, like, community. We talk about machine learning here. If we were, like, you know, forced to talk about our physics, we could just skip this entire thing here, right? I mean, like, you know, there's nothing we can talk about our physics. I mean, beyond Wikipedia level, right? I mean, I really don't. I love your pictures, but, like, you know, hell, what do I know? I'm not an expert at all, right? And the best thing is driven by other people's money. Like, you know, this is like my favorite one. Like, you know, as machine learning is driven, other people pay for it. I just need to play with the results. There's a nice results, a nice theory, like, you know, the 10,000 Einsteins. This is like Matt Schwartz. It might not be his original, who said, like, you know, if you want to think about the impact of machine learning and physics, said, like, currently, particle physics or fundamental physics, we're limited by the fact that we have only 1 Einstein per century, right? We would have to love more, but we don't. Now, if you take, like, you know, machine learning, and you enable people to do stuff, right? We'll have 10,000 scientists per year, per century, who can actually deliver, like, transformative stuff like Einstein did. And this is the way we win. But it means we need to work together, like, you know, machine learning and physicists need to work together. And then, yeah, the young people, they are the golden generation, right? Like a lot of things happening. Let me briefly advertise, if you want to learn more about this, my group is maintaining a set of lecture notes, machine learning for LHC physicists. I mean, read it and enjoy it, send us feedback. What might be even more important is there is a linked set of tutorials where we basically update and maybe maintain tutorials in Jupyter notebooks and PyTorch, where basically they are thinned out versions of a lot of research paper machine learning applications, including the data sets, and anybody who wants can play with them. Advertise that because I'm very proud of, I do the text here, but the group does all the tutorials, and the tutorials obviously way more important. Thank you.
Only one mic. Thank you so much, Tilman. It was fun talk. Questions, yes.
Yeah, thanks. Very interesting. So I used unfolding in a classical way, right?
Yeah.
And for me, the biggest issue was the bias on the simulation you take, right? So in some cases you have you have a simulation that agrees with data well, right? But what if you know that all your models that you have are not ideal, like none of the models is ideal? So how do you deal with let's say you talked about uncertainty earlier, how do you deal with the uncertainty in the bottom left, right arrow there?
Yeah. Yes. So, I mean, I just put this up because there's a nice paper on that one. So we're doing the same thing that the classical methods do. So we basically do a Bayesian iterative unfolding, where so you take your simulations, you unfold, you check for consistency between the two data sets, you train a classifier, you use that classifier to re-weight your simulations to be closer to the data, you retrain your network, you unfold again, you check if the whole thing is consistent. But that is, I think, literally the same as the Bayesian iterative unfolding that is used for classical methods. And you can basically generalize it. The advantage when you do it with machine learning is that you can implement this Bayesian iterative method through a classifier reweighting. So it's high dimensional unbinned. And classifier reweighting is total standard, it's very simple to do if you think about it. So we are basically, again, we're using the classical method, but there's no magic. We're using classical method, but classifier weight train.
Thank you for the very interesting talk. So I'm an astrophysicist, so my question is there any example, because I can see that unfolding can be applied in astrophysics, no? Instead of inferring in the observational parameter space, go one step back. Do you know any application of unfolding in astrophysics, or do you have any reference you can share with us?
Yeah. So in astrophysics, I don't know any, we're working on this right now. I don't know any reference where you go in between here. However, if you think about it, if you go right away, so if you do an unfolding in quotation marks all the way to here, to your theory, this is just, this is conditional generative inference. This is for instance, what Shirkopf does with the gravitational wave spectra. This is what, everybody is the Boston people are doing with inference, machine learning inference. So there, technically, they use conditional generative networks to go not to intermediate step to unfold, but they do the full inference. And this is something that in cosmology and astrophysics, a lot of people are doing. So we're working with Escape, friends on that. I should say it comes because of the different reliability of the simulations and the different data structure. It comes with a very different set of challenges, and a lot of things that for us in LHC physics are totally standard, absolutely do not apply to astrophysics, right? I mean, so it's not easily transferable. So when you actually use these techniques, you run into totally different problems. But I think it's the same thing. So and they are if you look into conditional generative inference by what's his name? Sharma, what's his name in Boston? He does this. Sid. Sharma, I forget his name, Sid. I'll give you later. Huh? Yes, exactly. Sid Mishra Sharma. He's doing exactly that, except that he is not interested in unfolding, he's interested in inference. Technically, though, it's the same. Yeah.
My question is actually has to do as well with will be comment what the question you asked. So one of the things we try hard to do in astrophysics is to back out the detector. And this really started in industrial scale some 20 years ago with large digital surveys where it was quite clear that we have the same problem. We have many more theorists than experimentalists or observers, and it's just impossible to forward propagate everyone's theory onto the actual observing plane. So we spend a lot of time trying to take the images as taken by any of the big survey telescopes and then transformed into what they would be above the atmosphere with a perfect detector.
Yes.
And that has led to a revolution in a number of things you can do with these data sets. So when the first big one was done some 20 years ago, it's now, I'll show that later in my talk, it's as cited as the Hubble Space Telescope. And it's this like dingy, 2-meter telescope in New Mexico. But it was because you could enable literally thousands of people to work on this same data set without having to know the details of that telescope or anything like that. Now, what we're trying to do going forward is this what you call here unfolding, like we just call it the very boringly data processing. It's to do that data processing, we need to have exquisite knowledge of the telescope, of the detector, of everything, which is really, really hard. We have too few people. So we're trying to figure out how to learn that through ML the same way you do. And I think there's a lot of potential for collaboration and like understanding what you were doing in AGP and how we can apply that to Astra as well.
Yeah, I would love to. I didn't know about this, like, yeah, I like what you did, data processing or deconvolution is also the same thing. Like, there's a million different words for the same thing. And yes, it would be great. And I really think like the problem in particle physics is that your field is already there. Everybody can analyze astrocosmo data in LHC physics. It's kind of silly, right? That our experimentalists say it can't be done. And they mean it, right? And then you compare the complexity of data LHC with astrocosmos stuff, as I said for SKA, and LHC is super easy. It's like it's almost trivial compared to LHC compared to SKA is absolutely trivial data, absolutely trivial. So I think there's a lot we can learn, and I think you're a success story. Yeah.
Yeah, just comment on the previous few comments. I think it's two sides of the same coin, right? It's in particle physics, it comes from a culture of you're trying to figure out the particle nature of some specific model. And before you build LHC, there's a huge effort to define what your theory of the universe will look like when you start making these new particles. But astrophysics, it approaches from a different direction, where you say, in the theory space, I'm trying to project down onto as simple of a model as possible, regardless of where I'm coming from. And so it's sort of a different, I think, sort of like, for lack of a better, sort of like cultural influence in how you look for new physics or try to do something like that. It's just a different approach to the same kind of problem. And I think doing a little bit of one in particle physics, more like astrophysics, or vice versa, can be very useful. And people haven't done things as much the same way in the two communities.
I think you're trying to give a physics reason for something that I actually think is sociological. I think the big experiments just love administration too much. And they quote this, and they quote the same result, I know this is like the Dan Hooper kind of story, right? They say, if we publish our data and somebody derives from it something, and this is wrong, it's our responsibility. But this is a pseudo argument, right? It's nonsensical. I mean, at the end of the day, it's the author of a paper is responsible for the mistakes in the paper, and not the people who provide the data or help them or talk to that person over coffee. This is a ridiculous statement. It is a ridiculous statement that is brought forward by CERN and the big collaborations over and over again. And as I said, in the second ridiculous statement life is too complicated, data is too complicated, which is after you can do unfolding, it's just simply also not true. I think so, like, it's basically, we're trying to justify something that is entirely cultural. Yeah.
Okay,
Exactly.
good. We are recording this.
Most of the people who know me wouldn't expect
Sure,
anything
sorry.
Like
Okay,
this.
thank you, Tilman, for the great talk. Okay, so we're running late, but let's meet 11:15. So let's